So, most of you have signed into mastering. I think most. I got one. But your first homework, because a number of you are having technical difficulties with it, I just changed the due date for the first homework. It was due tomorrow night. It's now due on Saturday. Gave you a few more days to help deal with if you're having issues signing in. You should have your code either through eCampus, so the bookstore, or through the course materials section on Blackboard. And if you're still having trouble with that, you probably need to talk with either IT or with David downstairs in the library. So that's the introduction and the physics primer. The homework on the first chapter and the first part of chapter 2. The first homework assignment, it's actual problems. That's due on the 10th. And the second homework will be due on the 17th. And we'll have our first lab today after lecture. So we're going to finish off chapter 2. And we'll have a lab after the lecture. Changed the way I set up working the problems, so hopefully that will be a little better. I typed up solutions and put them in slides, and I try to remember to replace the slides on Blackboard, because I don't think I've done that. But if you let me know if this is better or worse, because I can definitely stop doing this. So, continuing on from where we were talking about motion. We talked about motion with constant velocity. Now let's talk about motion with constant acceleration. So because acceleration is the derivative of velocity, if the acceleration is constant, the velocity will be the initial velocity, v0, plus acceleration times time. And your average velocity, when I made this slider, this particular slide got a little muddled. Let me see if I can quickly fix that. What are you doing? Oh, I see. I'll just move this over here. There, that will be fine. An average velocity will end up being the midpoint between the final velocity and the initial velocity. Because if you take the average of this line, it turns out it's the middle. So average velocity is 1/2 initial velocity plus final velocity. And given that average velocity is 1/2 initial velocity plus final velocity. Position is initial position times average velocity times time. So with a little bit of algebra, we get that position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. The other way you can generate the same equation is by taking the antiderivative of acceleration twice, if you want to do it the calculus way. But this is how to do it with algebra. And additionally, you can work out an equation for velocity as a function of position, where velocity squared is initial velocity squared plus 2 times acceleration times change in position, delta x. Delta x is final position minus initial position. So these three are the main kinematic equations that are used to describe motion. And most of the motion we deal with will be with constant acceleration. So, because of the fact that position is a quadratic equation in time, if we look at position versus time, it follows a characteristic curve. It's a parabola. So here we have something that's starting from 0 at rest and accelerating in the positive direction. It goes faster and faster. It's a parabola because it's constantly increasing its velocity, so it's constantly increasing its slope. So these are the equations of motion. Velocity is initial velocity plus acceleration times time. Average velocity is 1/2 initial velocity plus velocity. Position is initial velocity plus 1/2 initial velocity plus velocity all times time. Or more usefully, position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. And then lastly, final velocity squared is initial velocity squared plus 2 times acceleration times displacement, the change in position. Any questions about these? These are the primary equations you're going to be using. So here is a problem with these equations. We have a boat leaving a marina. It's traveling at 1.5 meters per second. So that's your initial velocity. And as soon as it leaves the marina, it accelerates at 2.40 meters per second squared. That's your acceleration. And after 5 seconds have passed, that's the time. How fast is the boat traveling, and how fast has it, and how far has it traveled? So I'll give you a few minutes to work on this, and then I'll go through the solution. So, in this case, let's start by going over what we know and what we're looking for. So we'll erase these. So what we know our initial velocity is 1.5 meters per second. Our acceleration is 2.4 meters per second squared. The time is 5 seconds. We're looking for two values: our final velocity and our final position, which apparently I put in a different place here. So let's start by finding the final velocity. So we're looking for velocity. We know initial velocity, acceleration, and time. That fits this equation. Velocity is initial velocity plus acceleration times time. So velocity is initial velocity plus acceleration times time. So if we plug in our numbers, velocity is 1.5 meters per second, our initial velocity, plus 2.4 meters per second squared times 5 seconds of time. Acceleration times time. And that's 1.5 meters per second plus 1.2 meters per second, or 2.7 meters per second. And you can see here, seconds cancel, and we go from meters per second squared times seconds to just meters per second. We also are interested in x. Oh, I did them as if they were two separate parts, that's fine. So x here, position, well, we actually know our initial position. It's 0. Because we're interested in how far it's traveled in those 5 seconds. So at time 0, it's at position 0. So we know x, x0, initial velocity, acceleration, and time. Well, we know initial velocity, acceleration, time, and x0, and we're looking for x. This equation is the natural one. Often you're looking for, how far something's traveled. That's going to be x minus x0. You can generally set x0 to 0. So the appropriate equation is x equals x naught plus v naught times t plus 1/2 acceleration times t squared. If we plug in our numbers, that's 0 meters plus 1.5 meters per second times 5 seconds plus 1/2 times 2.4 meters per second squared times 5 seconds squared, which comes out to 0 meters plus 7.5 meters plus 30 meters. You get 7.5 meters from the initial velocity times time, and 30 meters from 1/2 times acceleration times time squared. So if it wasn't accelerating, it would have gone 7.5 meters, and the acceleration makes it go an extra 30 meters. And that comes out to 37.5 meters. Which I should have rounded. No, I guess strictly that is. No, I should have rounded that to. Should have dropped that 0. That's what I get for typing this up quickly. So I'll fix that.
Wait, so are you multiplying? I thought you were multiplying the acceleration and the time.
It's acceleration times the time squared.
But in the first step, like the VO plus AT.
I did. I screwed up. Thank you for noticing my mathematical mistake when typing this up quickly. I'm sorry about that. So it's 13.5. Yeah, that makes more sense. Sorry about that. Again, thank you for pointing out my error. But that's for pointing wrong. That's what I get for writing this up. Any other questions about this? And I will be posting these slides from Blackboard. I haven't tell you that. So again, these are the equations for constant acceleration. And these are the three that are the most useful. Velocity is initial velocity plus acceleration times time. Position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. And final velocity is initial velocity squared plus 2 times acceleration times change in position. So these are the ones you use if you know about time, and either you're looking for a position or velocity. And this is the one you use when you don't have any information about time and you don't want to deal with it. So in general, if you want to solve a problem that you would use this for, you can actually use these two equations to get the same answer. You could generate this equation from these two, but it's a pain in the butt. So it saves you the trouble of having to go find what the time was and then plug it back in. So here we have a drag racer that starts from rest with an acceleration of 7.4 meters per second squared. So important things in this. The drag racer starts from rest. And we're looking at how far they have traveled. And here's our acceleration. And we're interested in how far it's traveled in 1 second, 2 seconds, and 3 seconds. So starting from rest means initial velocity is 0. How far it's traveled means you can take initial position as 0. Sometimes this equation also gets written as delta x equals v naught t plus 1/2 acceleration times time squared. Because delta x is just x minus x naught. And I have a few slides from another book that uses that format. Yeah, so here, like if I wanted to know, if I said, I have a car, I'm accelerating at, I don't know, 3 meters per second squared for 50 feet, for 50 meters. And I want to know how fast from start. And I want to know how fast I'm going at the end of that 50 meters. That's what I use this equation for. Notice how there's no time in that situation. So this is when you want to relate initial velocity, final velocity, acceleration, and distance traveled. And you're not interested in time. So if there is time involved, you're not going to use this equation. So here we have our knowns. We know our initial velocity is 0 meters per second because we started from rest. We know our initial position is 0 meters because we're interested in how far this drag racer has traveled. We know our acceleration is 7.4 meters per second squared. And we know our time is 1 second, 2 seconds, 3 seconds. We're interested in position. So, given that we know we're looking for position, we know initial position, initial velocity, acceleration, and time, we're going to want to use this equation. So position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. However, this is quite nice because our initial position is 0, initial velocity is 0, so those first two terms are just going to go to 0. So here, 0 meters plus 0 times 1 second, also 0, plus 1/2 times 7.4 meters per second squared times 1 second squared. That's going to be 3.7 meters. Because the first two terms go to 0 and the last term is 3.7. If we do it with 2 seconds, again, the first two terms go to 0. Now, instead of 1/2 times 7.4 meters per second squared, that's 1 second squared, it's times 2 seconds squared. So we get to 14.8 meters. And then if we do it with 3 seconds, we get 1/2 times 7.4 meters per second squared times 3 squared. And that is 33.3 meters. So in general, if you're dealing with position and time, you'll use this. If you're just dealing with velocity and time, you'll use this. And if you're not dealing with time, you'll use this. So here, this is a sort of problem where you're not dealing with time. You have a jet taking off on a runway. It accelerates from rest at one end of the runway, and it has to achieve takeoff speed before it reaches the end of the runway. So if flight A has an acceleration of A and a takeoff speed of V takeoff, what's the minimum length of runway delta XA? And if plane B has the same acceleration but twice the takeoff speed, what's its minimum runway length, delta XB? And finally, figure out what delta XA would be if acceleration is 2.2 meters per second squared and initial velocity is 95 meters per second. So the first parts of this are asking you to solve something symbolically, find an equation, but we know initial velocity, well, actually, this is final velocity. We also know initial velocity. And acceleration. So here's sort of a list of the things we know. We know our initial velocity is 0. Our initial position is 0. For the first part, our acceleration is A. Our velocity is velocity of takeoff, and we want to find what delta XA. We don't actually need the x0 equals 0. This is the equation we will be using. The way you would approach this, this is the situation for B. And then I think I did C with a different. So our equation is velocity squared equals initial velocity squared plus 2 times acceleration times delta x. So if we solve this for, and we know our final velocity is our takeoff velocity and our initial velocity is 0. So this is going to go away, and this we're going to plug in v takeoff. So if we solve this for delta x, so that's our C. I didn't. I wanted to get them all, and then I opened up another screen. That's why. For C is the actual numbers we're finding. So if we solve this for delta x, v0 is 0, so it's going to go away. V squared is going to be v takeoff. So this will be v takeoff. Acceleration is acceleration. Delta x is what we're solving for. So if we plug in our numbers, we have v takeoff squared equals 0 plus 2 times acceleration times delta xa. And so we can ignore the 0. We divide both sides by 2a. We get delta xa is v takeoff squared over 2a. If we do the same thing for B, well, instead of v takeoff, we have 2 times v takeoff. So we get 4 v takeoff squared equals 2a times delta xb. We divide both sides by 2a. We get 2 times v takeoff squared over acceleration. And for part C, we can use our answer from part A and plug in the numbers. So from part A, we know that delta xa is v takeoff squared over 2 times the acceleration. So if we plug in the numbers, 95 meters per second squared, that's our takeoff speed, divided by 2 times 2.2 meters per second squared. So 95 squared over 2 times 2.2, so it's 95 over 4.4. 95 squared over 4.4. That comes out to 2,051 meters. That's your, minimum run. Probably want something longer. Questions about this? Okay. So here's a similar problem being applied. Let's say you want to figure out what your braking distance is. You're in a car, you're traveling at some speed, you want to figure out how far your car is going to travel before it comes to a stop. If you know your acceleration, you can figure out your stopping distance. So here, if you're in a car traveling at 11.4 meters per second, and you suddenly see a deer, and the driver hits the brakes, and the driver will slow with an acceleration of 3.8 meters per second squared. So how long does the car take to come to a stop in both distance and time? So for the first part, for distance, you'll use this equation, because initial velocity squared, the velocity squared equals initial velocity squared plus 2 times acceleration times delta x. And then for the second part, you will use this equation, because that's telling you time. Final velocity is initial velocity plus acceleration times time. So I will give you guys a few minutes to work on that, and then I'll go over how you solve it.
Okay, which equation is time?
The first one, the one with timing. And now it is possible to use the first equation for time and then use the second equation here for distance. But it's a lot faster to just use this third equation and not deal with time to find the distance. So just important things to know. This is your initial velocity. This is your acceleration. And coming to a stop means your final velocity equals 0. So, did I forget to do this one? I think I forgot to do a write-up. Let me just. Yep. I forgot to do a write-up of this problem. So I will just work it out on the board, because I forgot. So first thing we want to do is figure out what we know. We know our initial velocity is 11.4 meters per second. We know our final velocity is 0 meters per second. We know our acceleration is minus 3.80 meters per second squared. And we are looking for x. And also t. So let's start with finding, well, delta x is actually what we're looking for. So let's find delta x first. So we know initial velocity, final velocity, acceleration, and we're looking for delta x. Well, this equation has initial velocity, final velocity, acceleration, and delta x in it. So we can use that equation. And so velocity squared is initial velocity squared plus 2 times acceleration times delta x. Our final velocity is 0. Our initial velocity is 11.4 meters per second. Quantity squared. We have plus 2 times acceleration. Our acceleration is negative 3.80 meters per second squared times delta x. We want to find delta x. We're going to subtract 11.4 squared. So we have minus 11.4 squared. The minus is on the outside. That's 2 times minus 3.8 times delta x. I'm going to drop the units for now. I'll put them in at the end. And then we can divide both sides by 2 times 3.8. So this is minus 11.4 quantity squared over 2 times minus 3.8. And that comes up to, well, 11.4 squared is what, 129.96, so negative 129.96 over negative 7.6. Gives us 17 point. Our delta x is 17.1 meters. If you wanted to work this out algebraically before you plugged in the numbers, I would plug in 0, but you basically get v0 squared over 2 times acceleration is equal to delta x. Now for time, velocity is initial velocity plus acceleration times time. So if we want time, velocity minus initial velocity equals acceleration times time. Time equals velocity minus initial velocity over acceleration, which will be 0 minus 11.4 meters per second over negative 3.8 meters per second squared. Time will come out to 3.0.
Where'd you get the negative sign from?
Where,
The 11.4, yeah.
because I have positive 11.4, and then I moved it to the other side of the equal sign. Or which negative?
Yeah, that negative.
This one?
No, yeah, the one you were at,
Over here?
yeah, that's.
Yeah, because I had positive 11.4 squared, and I had to subtract it from both sides to get it over on the left.
Oh, okay, gotcha.
Algebra, I got it from algebra.
Okay.
Oh yeah, this has actually got a minus. When I was, this is minus b naught squared, because d squared minus b naught squared over 2 equals delta x. Does everybody have this? Okay. we'll do a proper write-up of this and put it in the slides. So one of the most common cases of constant acceleration is gravity. And the nice thing about gravity is that acceleration, that constant acceleration, is the same for everything. Everything falls with the same acceleration. This acceleration, we refer to the acceleration due to gravity of the Earth's surface as g, little g. There's also a capital G constant. That's the constant that helps you figure out how gravity is, the strength of gravity in general for any two objects. But the acceleration of gravity on Earth's surface is little g. And it actually varies depending on where you are. So it will vary with latitude. So at the North Pole, it's a little bit higher. It's 9.832. In Norway, at 60 degrees north, it's about 9.819. In Hong Kong, at 30 degrees north, it's 9.793. And at the equator, it's like 9.780. So it does depend on where you are on Earth. Basically, because the Earth is spinning, that reduces it a little the further away you are from the axis. The book uses 9.81. I mean, yeah, 9.81. I've been trying to keep consistent with that with these write-ups, but my reflex is to use 9.80 because that's the number that I used when I was learning. Because it varies a little. So I'll give it on tests as a constant. I'll generally give it as 9.80 for tests and for tests. Usually that the difference between 9.81 and 9.80 is not a big enough error to get problems wrong, but the book does use 9.81. So any falling object is actually affected by air resistance. That's why, you know, in reality, if I take a piece of paper and a pen and drop them, the pen falls much faster than the piece of paper. But if I remove the air, then they would drop it the same way. Or if I reduce the air resistance by, say, wadding up the piece of paper, so it has a similar air resistance to the ball. So free fall from rest. Every second, your speed downwards is going to increase by 9.81 meters per second. So after 1 second, you're going 9.81 meters per second. After 2 seconds, you're on 19.6 meters per second. After 3 seconds, 29.4 meters per second. And after 4 seconds, 39.2 meters per second. And then your position, falling the distance you've traveled, you can use this to figure it out. So you've fallen 0 meters, 4.91 meters, 19.6 meters, 44.1 meters, and 78.5 meters after 4 seconds. You get moving fast. Additionally, if you throw something up, like so, it's going to slow down and come back down to your hand. And that process is symmetrical. Takes the same time to go up as it does to go down. This is a parabola in position versus time. And it also turns out your velocity at any height will be the same speed, but opposite directions. That comes from this equation. Because if you have two things at the same height, delta x is 0. So this term goes away, and you're just left with v0, v initial equals v initial squared equals v final squared. So either they're the same, or it's negative. So if you start at 29.4 meters per second, After 1 second, you'll be going at 19.6. After 2, you'll be going at 9.81. After 3, you'll reach the peak at 0, and then you'll come down. You'll be at negative 9.81 meters per second, negative 19.6 meters per second, and negative 29.4 meters per second. And this is a plot of position. It's a parabola. Your maximum peak position will be 44.1 meters high. So here's a rough solution guide for solving problems for projectiles if variables are known. This is written in Y because this is actually half of a chart for the two-dimensional situation. But everywhere you see Y, you can think X. It's just different variable. So if you want to find delta Y and you know initial velocity and time, this uses V initial for initial velocity instead of V zero. You end up taking biomechanics next semester. It's from that textbook. You want time. You want this equation. Yeah, so this lets you figure out which equation. So here, if we have a lemon that drops from a tree and it falls to the ground. So the important thing that is always the case, we have G is 9.81 meters per second squared, and it is down. You know, that acceleration points down. So often you end up using a negative G as your acceleration. Because if you're measuring, if going up gives you a bigger, if your positive direction is up, then your acceleration is negative G. Because your acceleration is down. Does that make sense? So if this way is up, the acceleration on the falling object is down. So it's negative. So if a lemon drops from a tree and falls to the ground 3.15 meters below, how much time does it take to reach the ground? And what is its speed just before it hits? So you'll be using the answer to the first part in the second part. You could use this for the second part, but once you have the time, it's easier to use the first equation. So I'll give you a few minutes to work on this. So just, I will put in what we know. I'll go over what we know. We know our initial velocity is 0 because we're just dropping something. We know our initial position is positive 3.5 meters. We know our final position is 0 meters. And our acceleration is negative G, or negative 9.81 meters per second squared. And for the first part, we're looking for time. For the second part, we're looking for final velocity. So the approach we'll take here, we're looking for time. So to figure out time, we know initial velocity, initial position, and final position. We're going to use this equation. For the second, we're looking for velocity. So x equals x naught plus v naught times t plus 1/2 acceleration times t squared. So we can plug in our numbers. 0 equals x naught plus 0 times 1/2 minus gt squared. This is sort of the general case for any dropped object, how long it takes to hit the ground from some arbitrary height. So 2 times x naught over g is t squared. So t is going to be the square root of 2 times x naught over g. In general, when you're trying to find time in one of these, you can plug in your values and use the quadratic equation. You might have to move your final position over so you have 0 equals something, but yeah. So if we plug in our numbers, 2 times 3.55 meters over 9.81 meters per second squared, and all square rooted, we get 0.801 seconds. And if we look at our speed is our initial speed plus acceleration times time. So that's 0 plus negative 9.81 meters per second squared times 0.801 seconds, which gives us negative 7.86 meters per second. How did that end up down? Sorry. Everybody got this? Okay. Everybody good? We'll continue. So here, this is a conceptual question. If drops of water detach from a leaky faucet at a regular interval and fall from rest, so they're all falling with constant acceleration. As the drops fall, does the distance between the drops increase, decrease, or stay the same? So the time between the drops will stay the same. However, the distance, the physical distance between them will actually increase. Because as they fall, they're going faster and faster. So in the same amount of time, they're going to cover longer and longer distances. So it will increase. Velocity is initial velocity plus acceleration times time. So as time increases, so does velocity. So the spacing increases. So therefore, so does the delta X between drops. Sorry. So here we have a volcano. This volcano spits a lava bomb up into the air, and then 4.75 seconds later, it crashes back down into the volcano at the same height it was released. How high above the point was it fired upward? The point it was fired upwards does the lava bomb reach? So this, to solve this problem, it helps to think about that parabolic shape. Because then we can break the problem down into like smaller pieces. So we know that something goes up and back down. It's a parabola, it's symmetrical, and it's going to reach its point. So, you know, this is p equals 0. This is p final. This is going to be 1/2 g final. Let me just put this real quick. I will roll. Just want to see how much is okay, not much. So zoom. There's this problem and another one, and then we're done. I'm moving to do the lab. So for this problem, what do we know? We know, why are you not going? Our initial position, our final position, and our total time. What we want to know, we also know that acceleration is minus g, and we know our maximum height. That's what we want to know is the maximum height. So we know the initial and final position. Using that, we can figure out that the initial velocity has to equal minus the final velocity. And that means that the time of maximum height. So if we think about the top point at the maximum height, what do we know about that? Well, we know the velocity at the top point is 0. And we know that the final velocity minus the initial velocity, the final velocity equals minus the initial velocity, sorry. By symmetry or by using this equation. Because if delta x equals 0, final velocity squared equals initial velocity squared. One is on the way up, the other is on the way down. So final velocity is minus initial velocity. And by symmetry from this structure, we can figure out that the time that you reach the top is 1/2 the total time. So now we want to figure out this distance. Well, we could try and figure out looking at the way up. But the distance on the way up and the distance on the way down are the same. So let's just work with the distance on the way down from the top, the second half. So we look at the second half where the lava bomb is falling from the top until it hits the ground. And that goes from half of T-top to T-top, so it's 1/2 T-top. So if we consider the second half of the arc, we go from X max back to our X0, which is 0 meters. The velocity of the top is 0. The time it takes to fall is 1/2 the total time, or 2.375 seconds. And now we can figure out the distance we've traveled using this equation. X naught is X max, our highest height, plus V top times time fallen, plus 1/2 G times time fallen squared. So if we solve for X max, well, we know X naught is 0, we know V top is 0, so those two terms go away. So this is 0, this is 0. Then if we solve for X max is 1/2 G times the time to fall squared. So that's going to be 1/2 times 9.8 meters per second squared times 2.375 seconds quantity squared, which is 27.7 meters. So to work this out, you got to think about the path the lava bomb takes and realize that you're dealing with this second half. It's actually, yeah. I don't know. Yeah, so that's the way to approach it. There are some other ways you can do it, but I think this is probably the most efficient one. Any questions about this? So here we have a little more straightforward problem in some ways. Well, you have the less sideways thinking. We have a diver that jumps upwards from the top of a 10-meter platform at 3.3 meters per second. How long does the diver take to reach the pool? So this you are starting. This is X naught. Your final position is 0. This is V naught. And what is the maximum height of the diver? So to figure out the time you reach maximum height, X max, at X max, V will equal 0. So at your maximum height, your velocity will be 0 because that's when you're turning around. You've come to a stop and you've started to fall back down. So I'll give you, well, we don't have that much time left for the class, so I think I'll just, you're okay with me just going through this? Okay. So what do we know? We know our initial position is 10 meters up. We know our final position is 0 meters. we know our initial velocity is 3.3 meters per second. So we want to find the time it takes to reach the pool. We also know our acceleration is minus g, and we want to find the time it takes to reach the pool. So we're going to use this equation here, and we're going to solve for time. And then again, we're going to find x max. So first, we're using this. I definitely feel like I screwed up the animations on this slide. I did screw up the animations on this slide. Now they are fixed. So we're going to use x equals x naught plus v naught t equals 1/2 at squared. We'll start by plugging in our values. 0 equals 10 meters plus 3.3 meters per second times time plus 1/2 times negative 9.81 meters per second squared times time squared. And we want to find out what time is. Well, this is a quadratic function set equal to 0. There's a formula for that. So first, let's clean up everything. This and hide the units. So this is 10 plus 3.3 t plus 4.905 t squared. That is not a plus. That should be a minus. That was a typo. And that means I need to check that I got the right answer, but I'm pretty sure I did. I think it's still sitting in my polysolver. Yeah. So this is a quadratic equation. I mean, this is a quadratic. Well, we can plug this into the quadratic formula, which I guess I just sort of skipped over, but the quadratic formula, x equals minus b squared plus or minus square root of, no, minus, why am I not remembering? X equals minus b plus or minus square root of b squared minus 4ac all over 2n. There. That's the quadratic formula. It gives you two values. The two values you'll get out are negative 1.13 seconds or 1.8 seconds. Obviously, it didn't take negative time for you to reach the pool. So the time is positive 1.8 seconds. So this is the correct answer. So at x max, v equals 0. So we can do another calculation with v equal to 0. So we can use this formula because we want to find x max. X max is just going to be x naught plus delta x. So v squared equals v naught squared plus 2a delta x. 0 squared equals 3.3 meters per second squared plus 2 times negative 9.81 meters per second squared times delta x. A little bit of algebra, you get 3.3 meters per second squared divided by 2 times 9.81 meters per second squared. And that equals delta x. and that comes out to 0.555 meters for delta x. But we started at a height of 10 meters. So x max is x naught plus delta x. So 10 meters puts 0.555 meters, 10.55 meters. So that's the last problem for the chapter. I'll give you guys a chance to note it down.
You said you're gonna upload all these and stuff?
I'm gonna upload these slides, yes.
Okay.
But I should put the solution for that one I forgot in. So just a summary of chapter 2, distance is the total length traveled. Displacement is change in position. Average speed is distance over time. Average velocity is displacement over time. Instantaneous velocity is average velocity measured over an infinitesimally small time. Instantaneous acceleration is average acceleration measured over an infinitesimally small time. Average acceleration is change in velocity divided by change in time. Deceleration is when velocity and acceleration have opposite sides. When you have constant acceleration, these are the equations. They relate position, velocity, acceleration, and time. And for freely falling objects, they have a constant downward acceleration of 9.81 meters per second squared, which is usually negative, but it depends on your coordinate system. And that is chapter 2. So I am going to stop sharing and end the meeting, and we'll get started on the lab.